Okay, thanks for coming to watch my talk. I'm Yumbom. I'm going to talk about how to do log concave sampling from scratch in high dimension, much faster than the previous algorithms. And this is joint work with Vempala. Yeah, and to begin with, let me start with very simple but important special case of this problem, which is a polytope sampling. Your goal is to simply pick any point randomly, and also equally likely within a polytope. And then this simple problem has found many applications, for example, in system biology, but especially in the context of theoretical computer science (TCS). This uniform sampling has been a important subroutine for volume computation algorithm, which was essentially initiated by Dyer-Friis-Kanaan. And then there have been many researchers working on this problem. And this polytope sampling actually can be studied in more general way through uniform sampling from a convex body. Here, convex body means that your set is convex and compact and not empty interior. And then also you assume that you have access to a membership oracle for a convex body K, and which tell you your curry point X is in K or not. And actually, you can implement your membership oracle for a polytope by manually checking linear equality for a given curry one by one. Okay. And then here is a more precise setup description. So you can always assume that your K convex set contains a unipole inside, and its diameter is d. And then you can do so because you can always translate and scaling, and you can standardize a problem setup. And like I said, you assume that you have access to membership oracle. So your algorithms along its iterations will probably carry many points to this membership oracle, and this membership oracle tell you your curries are in K or not. And in this setup, let me make it more further precise. K is convex body, and phi is uniform distribution over K, and epsilon is target accuracy, and D is a desired metric and divergence. And given this setup, my question is, how many curries does your algorithm need to generate sample X such that its law of X output is epsilon close to your target phi in your chosen metric D, which can be TV, KL, chi-square, whatever you want. And in this setup, the sampler's curry complexity is simply how many curries do you need, okay? And sampler's total complexity is this multiplication of this curry complexity times this per step arithmetic operation, okay? And then when people are studying this problem, people instead study two solved problems together. The first one is sampling from warm start, and then the second part is warm start generation. So here, warm start means that your initial distribution is already close to your target distribution. And given this warm start, how many curries do we need to sample from our target distribution? And then the second question is how to generate this good warm start. Okay. And then state-of-art results will be discussed in this slide, but I will focus at this moment. I will focus on isotropic convex body K. Where isotropic means that your convex body has center at the origin, and its covariance matrix with respect to uniform distribution is identity. So K basically looks very well-rounded like this. And for the first problem, warm sampling from warm start, it is known that D square is enough through the bulwark, this bulwark was developed by Lovász-Simonovic, and it was properly analyzed by Kanaan Lovász-Simonovic in 1997. And thanks to a lot of nice progress on the Kel's conjecture, the well-known complexity is now D square from warm start. And then for the second question, a warm start generation, it is known that D cubic curries are needed through the bulwark to generate this warm start. And then this was done by cousin Vempala almost 10 years ago. And then our main motivating question in this talk and work are basically these two questions. The first one is, okay, can you sample from isotropic body faster than this D cubic? Okay, so currently the bottleneck is this D cubic part, warm start generation, but can you make it can you break this cubic barrier? Which is our first question. The second question is, so far we have only talked about uniform sampling from a convex body, which is a special case of a log-concave distribution. But our second question is, can you make it more general, like generalize it to log-concave distribution? Okay, these two questions are the main things that we discussed in this talk. Okay, so for uniform sampling from warm start, there have been some classical algorithms such as bulwark and hit and run, and these algorithms have been discussed and used as default algorithm. But recently, in and out was developed, which is a special case of proximal sampler. And I argue that this algorithm is better than the bulwark because it is much simpler and also cleaner than this previous classic. And this in and out is basically consists of like two inner steps. The first one is forward step. Suppose you're at x1 here, then you just add a random Gaussian to this xi. So this forward step might take you outside a convex body K, but that's fine because through the backward step, you can make sure you can come back to this convex at K. And then this backward step corresponds to this Gaussian centered at y2 here, but truncated to this convex at K. Okay, and it's a bit tricky to sample from this distribution, but you can still do that through rejection sampling. You just keep on drawing some new point xi plus 1 centered at yi plus 1 Gaussian until this new proposal fall inside of this convex body K. And you can actually check that the condition on this success, this proposal actually follows this distribution. Okay, and then like I said, this one iteration of in and out is a successful completion of the one forward and one backward step. Okay, and then before talking about the main guarantees of this algorithm, I'd like to recall some important hierarchy of probability divergence and distance. So like to begin with, let me talk about Q rating divergence. Here Q is a parameter, rating parameter, which range from 1 to infinity. So roughly speaking, rating Q divergence for two probability measures is simply some coefficient time log of LQ norm. Okay, so yeah, just roughly speaking is log of LQ norm of the relative density of mu over phi. Okay, and then throughout this talk, I'm gonna just use the notation MQ to denote this this relative density, and then is LQ norm. Okay, and then a well-known property of rating Q divergence is that it's increasing in the rating parameter Q. So rating Q is bounded by rating infinity, and also even if rating Q is finite, rating infinity could be infinite. Okay, and the rating infinity is just log of the m infinity. Okay, like basically the log of the bound on this pointwise the ratio bound. Okay, and the rating Q is larger than rating 2 when Q is larger than 2, and the rating 2 recovers some chi-square divergence through this equality, and then rating 1, which should be understood as a limit, recovers KL. And then through pin-square inequality, we know KL bound TB square. So basically, the point is the rating Q is sort of like unified notion that allows us to talk every like well-known like notion of probability divergence like KL chi-square. So from now on, I'm going to just focus on rating Q and then just describe everything in terms of rating Q guarantee. So main takeaway from this slide, only thing you should remember from this slide is rating Q is increasing in Q. Okay. Okay, so let me just recall some theoretical guarantee for in and out that was established in earlier work. So when phi 0 initial distribution is m infinity worm with respect to phi, which means the pointwise ratio between this phi 0 initial distribution and target phi is bounded by m infinity, then in and out require this many curries for rating Q guarantee. This means that your final sample is epsilon close to your target phi in rating Q divergence. Okay, and here lambda is the largest eigenvalue of covariance matrix of phi, and like I mentioned a little bit earlier, this lambda basically captures like how skewed your convex body K is. So if your convex body K is very skewed like that, then lambda is likely quite large. But if like your phi, your convex body is isotropic, well rounded, then lambda is just 1. Okay. And then worm star generation problem has come to the picture, because if you just naively use some easy worm distribution, then m infinity gonna be very large, like exponentially large. So worm star generation problem is to generate some good initial worm star whose wormness is gonna be O1. I will get back to this part. And then here is like some comparison between bulwark in and out. And let me explain this notation first. So this notation means that in order to get bulwark's guarantee, your initial wormness is given in terms of random infinity, and because random infinity is equal to log of m infinity, so I'm just focused on random infinity instead of m infinity here, and the final guarantee is given in terms of TV. Okay, so in order to get TV distance guarantee, your initial warmness should be random infinity, and then the final Curry complexity is given by this one. Okay, but on the other hand, in and out's initial warmness still random infinity, but it's like a given final guarantee as a given in random Q. Okay, and it looks like this. So in some sense, random in and out's guarantee somehow interpolate this generalize this bulwark's guarantee to like random Q divergence, right? And then here is some pictorial illustration, like when bulwark's initial distance, initial warmness is given random infinity, is the target is somewhat like weakened to TV, and in and out is still has this sort of issue, but way better than bulwark because its final guarantee is given now in random Q, stronger than TV, right? And one of our main contributions in this paper is that we refined analysis in and out so that the initial warmness is now not random infinity. It's now much weaker than random infinity. So we relax to random infinity to random O1. Okay, and like I said in the a few slides earlier, so random O1 is smaller than random infinity. So now in order to invoke some in and out guarantee, the initial warmness, the level of initial warmness is much more relaxed. Okay. So in and out guarantee now require much weaker warmness. And then to get this result, actually this problem, the complexity of this problem comes from two sub-problems. The first one is like the number of curries for each backward step, per iteration. So in the backward step, remember that we use the rejection sampling to implement this to implement this line, right? And then every single time we check that the proposal, whether this proposal line in K or not, we actually need to use one curry to the membership oracle. And then ideally, each backward step should be done within O1 many curries per step, right? And then the second step, the second part is simply the number of iteration of these in and out to be epsilon close to your target distribution. So this is a required number iteration, and this is a per step complexity. And then by multiplying these two vectors, we can establish the Curry complexity of in and out. Okay. And then let me explain why we should take h to 1 over d squared to make sure the backward step can be done in O1 many steps here. So the main important result in here is some concentration result. So K is convex body in RD containing unipole inside. Then what we know about this phi convoluted with Gaussian is this one. So K plus B delta, here B delta is a ball of radius delta. So K plus B delta is basically here this region, okay? And then what this inequality says is the following. Suppose you're already starting from the your uniform distribution from xi, and then after taking the fourth step, the fourth step take you to yi plus 1 by adding Gaussian, and then it is to see that this yi plus 1 actually follows the distribution obtained by phi convoluted with this gamma H, okay? And then what this inequality says is that after taking the forward step, like how far should we go from this K, which is delta, to recover the most of the mass of the forward distribution. So I mean, I wanna find like delta and H such that after taking the forward step, your most of the forward mass should appear in this yellow region plus this green region with like 0.99. So from here, it actually makes sense to take delta to 1 over d because we want to make this exponent like 0.1, right? Like minus 0.1. So like delta should be 1 over d. And once we take delta like that, then h should be like 1 over d squared, right? And by changing the like multiple coefficient properly, we can make sure the right-hand side is going to be 0.99, okay? And if do so, once we ensure this, then we can do some calculation to show that all many curves are actually enough for rejection sampling until the first success. When starting from the stationary distribution phi. But remember, we are actually starting from some Wormstar distribution, which is slightly deviating from this phi. So this initial like deviation, like M01 warmness, like end up like introducing some M01 overhead in the final complexity through Hölder inequality. So that's why under this step size, h1 over d squared, we need this many curries trier for each rejection sampling. Okay. Now let me move on to the second part, mixing rate. And to begin with, let me recall you this Poincare inequality. So this Poincare inequality is sort of function inequality that basically measures like some variance of your distribution phi. So here CPI is called Poincare constant of your target distribution phi. And then this Poincare constant is defined as the smallest possible constant that make this inequality satisfied for any like test function like this like locally lattice function. And then the well-known result about this like in and out sampler or proximal sampler in general is that each iteration of in and out decreases Rennie-Q divergence by this much. And then in order to make it like smaller than epsilon, we can do simple algebra to show that this many iteration is actually enough. And we know that like h should be 1 over d squared, right? And then the next question is what should be this CPI of uniform distribution, Poincare constant of uniform distribution? And then here is where the Kel's conjecture comes in. So they posed that this Poincare constant of the log-concave measure phi is actually within some constant of the largest eigenvalue of covariance matrix of phi. Okay, and then the current the best bound is due to Klaatop. He showed that this conjecture is true up to some log vector. So putting these things together back to here, so final complexity looks like qd squared times lambda, like up to log. Okay, and this result, this Klaatop's result on Poincare constant was achieved through a stochastic localization. And then just for your information, and Santosh will talk about this localization method, like including classical localization as well, in the workshop on December 14th. So feel free to attend this workshop. Yeah, and then so far we have talked about the first problem, like how can you sample from warm start, and then we just finish it. And then now let me move on to the second part, like how to generate those warm start. So in and out's complexity now is this. And yeah, and then in order to get some polynomial Cauchy complexity bound, we need a like good warm start, like which means M01 should be small enough like 01. So, but for example, like if you take like some easy but bad distribution as a like initial starting distribution, like small ball uniform distribution over small ball inside K, then your warmness parameter is exponentially large. Okay. So that's why we like tackle like this warm start generation problem more seriously. And then from now on, for a moment, let's say K is isotropic for simplicity, but now I'll visit the more general case later on. Now the goal is to generate some sample Z whose law is very O1 close to phi distribution in any O1 divergence, which is our goal. And then the classical approach is annealing approach. So annealing is just like following some sequence of distribution, and then gradually following this annealing distribution toward your target distribution phi. And there are some desirable things that you want to ensure when designing this annealing distribution. For example, like mu0 should be easy to sample from, so that you can easily get in this annealing distribution. Okay. Also, when you move from mu I to mu I plus 1 along this annealing sequence through some samplers, ideally mu I should be close enough to mu I plus 1, like O1 warm, so that transition from mu I to mu I plus 1 is fast enough. Okay. And then classically there have been many annealing distribution proposed, such as uniform annealing and exponential tilting and Gaussian as well. And then in this talk we particularly focus on this Gaussian annealing, and this is called a Gaussian cooling algorithm. So each mu I annealing distribution now looks like a Gaussian distribution truncated to this complex at K. But along the way, you want to increase sigma I square, but as large as possible, but also slowly enough so that any two neighboring distribution is close. Okay, and also in order to move across this annealing distribution, you actually need a sampler in and out for a truncated Gaussian distribution. Okay. And then it turns out you can adapt the in and out algorithm for truncated Gaussian, not just uniform distribution over complex at K. And then the correct complex result almost look similar to this uniform distribution over complex at K. So K is convex and accuracy is epsilon and step size d 1 over d squared. Then in and out guarantee for truncated Gaussian, we can show that its complexity looks almost similar. And the only difference is that we replace lambda, the largest eigenvalue, by sigma square, okay? And which is more or less obvious from Vempala inequality. And before we develop this in and out for truncated Gaussian, cousin Vempalas, when they designed this Gaussian cooling algorithm, they adapt the Bullock algorithm for Gaussian sampling as well. And then this Bullock for Gaussian also looks its guarantee look also very similar to Bullock's for uniform sampling. Its initial warmness should be random infinity, and its final guarantee is given in TV. But their final guarantee looks slightly more a bit complicated. As you see here, there is some some analytical artifact like the maximum term here. But on the other hand, our algorithms in and outs final curve complexity looks much cleaner. And it doesn't have some analytical artifact like that. Yeah, and this is a comparison between their Gaussian cooling algorithm and our new algorithm. And then for isotropic K, their complexity, Gaussian cooling complexity is d cubic, whereas our algorithms, the faster warmth generation takes complexity d to the 2.75. Okay. And then in their Gaussian cooling algorithm, in order to invoke the complexity of the Bullock, which require any infinite warmness, they need to take some sort of conservative update to ensure any two distribution is close in Rennie infinity. But on the other hand, we know that now in and out's initial warmness only should be enough, Rennie 2 warmness should be enough. So we can take more aggressive update like that. Okay, so that we can ensure that any two neighboring distribution is close in Rennie O1. And like I said, this the benefit of this newer algorithm comes from this more aggressive update. Because we no longer need Rennie infinity, we are just happy with Rennie O1, so we can take more aggressive update like that. And then and the second benefit of this algorithm improvement comes from faster mixing of in and out because of our new improved log inequality constant. Here, log inequality looks very similar to Poincare, but unlike Poincare inequality, log inequality care more about like entropy instead of variance. And the LSI constant is basically the smallest possible constant that satisfies this inequality for any test function f. Yeah, so like here, let me just tell you some more main result of our work. So like, so even though I previously tell you like in and out mixing looks like d squared times lambda squared, this thing can be actually written in more general way, like d squared times LSI constant of the mu sigma square, which is annealing distribution whose like variance is sigma square. And then the first result we established in this work, is that LSI constant of log concave probability measure phi with the finite support of diameter d is turned out to have a better bound, which is d times square root of Poincare constant. Maybe it has some log factor, but we just ignore log here. Previously, it was just d squared, which was established by Friesen-Cannon. And but we just improved this to d times c Poincare, square root of c Poincare, and it is on the the Poincare constant is d squared. So apparently d times square root c Poincare is a improved bound than this classic bound of Friesen-Cannon. And then to achieve this result, we use anisotropic stochastic localization. And the second result is this a bit more complex geometric result. So when suppose consider this distribution, standard Gaussian, truncated to isotropic convex by K, which basically looks like this. And by Braskamp-Lieb, we know that this the largest eigenvalue of this distribution is basically bounded by 1. And then as you increase sigma square, then you can feel like this increasing sigma square make this distribution more flat, right? So when sigma square is large enough, you may feel that this truncated Gaussian looks very similar to the uniform distribution. So, and then because now it's very close to uniform distribution, is largest eigenvalue of covariance matrix, or should be very close to the covariance matrix of this uniform distribution as well. And then we show that this phenomenon is actually true when sigma square is larger than square root d. Yeah, and then we use some complex geometric hammers, like a large division inequality by Paris, and small wall probability, and some tangential phenomena. Yeah, so here's a summary. When sigma square is larger than square root d, so in and out mixing, which is written in general d squared times log sublog constant, is bounded by d squared times lambda, because CLSI is, according to our first result, is roughly d times square root of c Poincare, right? But we know that c Poincare is bounded by log lambda times log d due to Klattok's result on the Keller's conjecture, and then we know that this lambda is O1, right? Because when sigma square is larger than square root d, according to our second result, lambda is O1, right? And then we may assume that d, this diameter, is smaller than square root d by some suitable truncation of a convex at k due to isotropy, so that d is this bound is basically square root d up to some log. So in and out mixing, when sigma square larger than square root d, is always d to the 2.5, and then apparently this is always better than d squared times sigma square, right? And then, yeah, here is a summary of these algorithms and complex analysis. And according to this update rule, in order to double this initial sigma square, we basically need square root d over sigma many phases to double initial sigma square, right? And each phase before sigma squared less than square root d is, like I said, d squared times sigma squared. And so that like complexity of sigma doubling is simply just multiplication of these two things. So we obtain d times 2.5 times sigma, and then this is true up to sigma squared less than square root d. So that's how we got d to the 2.75. And even after sigma squared larger than square root d, we know that the in and out mixing is always d to the 2.5. And multiplying by this and this, we can make sure this complexity is all d to the 2.75. So adding this all up, total complexity of this process is simply d to the 2.75. Okay, improving this d cubic complexity of cosmic Vempalas. So far, we have talked about isotropic convex body, but actually this can be generalized to general shape convex body as well. So like convex body sampling from warm star can be generalized like that. This is already like what we covered in the first part of talk. And especially for warm star generation, we have more general bound like that. Here R square is a second moment of our distribution. And especially when this distribution is isotropic, lambda R square, which is just d, because this is trace of covariance, so it's just d. So that what is that? This is like d 75, and then when phi is isotropic, this is 1. So that this recover d.2.75 result that I told you. And now it's time to generalize to general log concave distribution. Log concave distribution is simply just like some distribution whose density is proportional to e to the minus v, where v is convex function. So when you take a log here, then you will be left with minus v, and then when v is convex, this is concave function, right? So that's what we call it, like log concave distribution. And then just as we work with the membership oracle for uniform sampling from a convex set, we sort of need like some proper generalization of this membership oracle, which we call like zero sort oracle or evaluation oracle for V. And if you carry point X to this oracle oracle tells us the value of V potential function at each carry point X, right, up to some fixed attribute constant. So under this evaluation oracle, you don't need to know the normalization constant of this e to the minus v, okay? And then you might be wondering why we care about this particular setting, like those order log concave sampling. And the first reason is that this is a very general setting. It does not require gradient separation oracle. So you can always like use this algorithm in general setting, like, and you can use this algorithm as a default algorithm. And theoretically, once we have a concrete understanding of the current complexity of zeroth order log concave sampling, we can treat it as like theoretical baseline, so that like we can highlight like the benefit of working with extra assumption. Suppose when you have access to gradient of V or like ellipticness of like gradient V, how can you further like improve the dimension dependence? You can ask this question more in a nice way, right? So in order to generalize in and out for this log concave distribution is a bit tricky, because like when you implement the backward step, it's a bit tricky to implement the rejection sampling. So we try to somehow like avoid this issue by borrowing convex some insight from convex optimization. So in convex optimization, so when you want to minimize convex function V here, people typically replace V by a new auxiliary variable T, and then instead people append like new constraint like this, which is epigraph of convex function V, and then which is convex because of convexity of the function V. So your original problem is now simplified to some linear objective function subject to some convex constraint, right? But in one dimension higher space. And then my goal is we can actually translate this technique to log concave sampling setup as well. And this is called like exponential lifting. So when you want to sample from e to the minus v, a distribution phi x, which is a proportion to e to the minus v, you can replace v by dt. Yeah, you need some multiplicative coefficient here for better exploitation, for some computation, but it's not a big deal. So you replace v by dt, and then like append like this constraint as a constraint here. And then now your target distribution is simplified from this complicated general distributions to exponential distribution in one dimension higher space, right? And then you can easily check that the x marginal distribution of this and a d plus one dimension distribution is exactly phi of x. And given this observation, our strategy is very straightforward. We just sample from this x comma t from exponential distribution, and then because x marginal is exactly phi of x, so we can just keep the x part by throwing away t part, okay? And then now, because your distribution is exponential distribution, your backward distribution is still Gaussian, so you can use the rejection sampling with the proposal being Gaussian. So you can analyze it, and just establish some guarantee there. And then this is some pictorial illustration of this process. So by reduction, you go to like one dimension higher space, and then you draw you sample from this exponential distribution through in and out algorithms like this. Yeah, and then here is the extension to log concave sampling. Just as uniform sampling, it looks almost exactly similar to the uniform sampling guarantee, but we have some additive curry by taking the maximum with some constant, and which is also same for this Wormser generation problem as well. But for like isotropic case, this is 1 and this is 1, so this term is going to be just 1. So it's not that different from uniform sampling case. So yeah, this is how we extend it to log concave distribution. And yeah, and this is the end of my talk, and then thanks for watching this talk.